Thanks so much for the introduction. Thank you all for attending. Thanks to the VLSI and Photonics chapter for the opportunity to present our work on co-packaged optical I/O for data centers and high-performance compute. So before I begin today, I'm going to acknowledge a few themes. The material that I present today is a combination of research that's been done at our lab, Intel-5 Research, and our Silicon-Photonics product division, and our assembly and test team, ADDD. Okay. You want to close the door? All right. So here's an outline of the talk. We'll see how much we can get through today. So we'll start with a discussion on why silicon photonics is important for data center interconnects and high performance compute. I'll then give you a brief overview of intensity modulated links. I'll then talk about a subset of the photonic devices available in our silicon photonics platform, and then the companion electronics that we've developed to interface with this platform. And then finally, we'll talk about this important research vector, wavelength division multiplexing, that helps us to increase data rates in IMDD. And then finally, really a brief, overview of what we're doing now and in the future. And then we'll conclude the talk. So I was considering whether to crack this joke or not. I've decided to. So I'm going to start with two cliches. The first is that the sky is blue, right? As we all know, right? And then the second one is that, well, modern workloads are placing an increasing burden on interconnect. So you've heard this term a lot, right? And it's most probably because we all love to watch Netflix and we want to enable Skynet as soon as possible. Skynet, for those of you who don't know, is the doomsday AI machine from the movie Terminator. I recommend watching it. So AI workloads, what happens with AI workloads is that we expect them to span multiple nodes. And we need to have interconnect that can span these nodes with low latency, low power, and high bandwidth density. And the electrical SerDes that we all heard about right now, the challenge with data scaling approaches in electrical SerDes is that they're reaching certain limits. The first one is a bandwidth limit as you try to go beyond 100 gig SerDes. Now you could try and get around that bandwidth limit by using some of the equalization techniques that we heard about earlier, but many of them are very power hungry. And so as you can see from this picture, SerDes starts becoming an increasing portion of your total package power, right? So one way to get around this is by increasing I/O pin count. But as even the previous speaker mentioned, package sizes are becoming really large, and any further increases in sizes would come at a very unsustainable cost. So we need to find an alternative I/O solution, right? So at Intel, our proposed approach is optical compute interconnect, or OCI, in which we bring the optics into the compute package. So this can help us enable other interesting techniques to handle data-intensive workloads. For example, I've shown an example here. This is resource disaggregation. So the memory and I/O that is available in a typical compute node may not be sufficient for future requirements. Instead, what we could do is we could pool memory and I/O resources across multiple nodes so that you can have resources as you want them, whenever you want them. And also you're improving the overall resource utilization. So this is something that, for example, OCI could enable. This picture is basically how optical I/O has evolved at Intel. Our high volume product here is on the left. Okay. So our high volume product is on the left. It is a pluggable module for Ethernet, and it consists of many discrete photonics and electronics ICs inside this package. This can support up to 100 gig to 400 gig SerDes. In this case, the faceplate is still inches away from the actual switch. So you still need to do SerDes on that inches long interconnect, and that can still be quite power hungry. In 2020, we did this industry first demo of a co-packaged photonic engine. So this is a 1.6 terabits per second photonic engine that's been co-packaged with this switch. This photonic engine contains a PIC, which has an integrated laser and integrated optical modulator, and it's been co-packaged with SerDes ICs that we've got from off the shelf. And what this allows us to do is place the PE. The PE form factor is so small that we can place it much closer to the switch than a faceplate could be. The electrical channel is a lot shorter, and you don't have to do complex SerDes, which burns a lot of power anymore. The other advantage is because the packet size is so small, you can pack in multiple fibers. And so you can increase the overall bandwidth density. With OCI, we're planning to bring the optical compute even closer to the switch or the XPU by using advanced packaging techniques.
About the second,
part,
each of those pads is an interconnect link.
This is not a pad, this is a photonic engine.
Okay.
So you connect the photonic engine to the switch through this electrical service. And then you connect a fiber to the photonic engine.
So service is still there?
Yeah, this is the short service, okay, so but it is much shorter than it would be here.
Okay, so photonics in package, and now you are moving to photonics on chip.
Yes, not exactly on chip, but that's a good question. You'll see it on the next slide. So this is even closer, so the link would be even shorter, right? So this is an example of a packaging approach. So in this case, the XPU is connected to the OCI or the optical compute tile or the optical compute interconnect tile over EMIB. EMIB is an Intel specific term, but really it's just a low power dense parallel IO, right? So that answers your question. So inside the OCI, we have an EIC, which is the electronic integrated circuit, and a PIC, which is the photonic integrated circuit. The EIC contains all the SerDes that is necessary to drive the photonics devices. It also contains control circuitry to control all the photonic devices. And then the PIC contains all the optical components that you would need, for example, for optical generation, optical amplification, dense wavelength division, multiplexing, etc. And ultimately, the idea is that this PIC would connect to the detachable optical cable. Okay, so today's talk is going to focus on the OCI type, which consists of the EIC and the PIC. Now, the talk is pretty long, so I'm actually going to stop in the middle for questions at least once. So let's try and reserve our questions for those breaks, just so that we can, get through a lot of the material. Right. Okay. So coherent links is something you guys may have heard about. They're certainly an important area of research, but today I'm going to just focus on intensity modulated links. And I'm going to first talk about what components, electrical and optical, are required to make an IMDD link. So in intensity modulation, we're trying to transmit data on an optical carrier by encoding it in the amplitude of the incoming light. And we do this by using an optical modulator. This modulator is itself driven by a high-speed driver, right? So at Intel, we're experimenting with this heterogeneous integration where the PIC, or the photonic integrated circuit, contains all the optical components, and it's fabricated in our silicon on insulator foundry, which is Fab 11X. In-house Silicon-Photonics foundry, sorry, not silicon on insulator foundry. And the EIC is developed in a scale CMOS mode. You can put simple modulations like NRZ, on-off keying, on the light, or you can even do more complex multi-level intensity modulations to increase the data rate. Once you've placed the modulation on the light, you launch it on the fiber, and it reaches the receiver. The receiver is a direct detection receiver. It consists of a photodetector, which converts the incoming light into a photocurrent that is then electrically amplified so that you can recover the transmitted data. One important problem with co-packaged optics is the thermal temperatures that the high temperatures that you can reach. So thermal management is an important problem. It's an important research vector, in fact. And what we can do is, because we are co-packaging it with CMOS, we can leverage this dense CMOS logic to develop control circuitry that also tries and maintains the performance of these photonic devices. So our team, Phi Research Lab and SPPD, of course, but I'm talking specifically right now about Phi Research Lab, has innovated in all of these areas. We developed the circuits at Intel Oregon, and we developed the photonic devices at Intel Santa Clara. I myself am a circuits designer, and what I'm going to do today is provide a photonics overview, which is really a field guide for the wireline engineer. So I'll try and answer your questions as best as I can on that, but at least the circuits portion, I'm hoping to answer more. So with that disclosure, let's start the talk. So the first thing that we're going to talk about is the optical modulator. So like I mentioned, the optical modulator is what is responsible for placing the intensity modulation on the light. It transitions between two states, one which lets light through and one where it is attenuated, right? The optical modulator transitions between these two states with the help of the voltage swing provided by an electrical driver. The larger the driver swing, the larger the optical eye opening or optical modulation amplitude. And what we would want is this driver swing to be compatible with CMOS so that you could enable high volume manufacture. The second metric that you care about in an optical modulator is the modulator bandwidth, because this limits the total data rate that the highest data rate that you can put on the incoming light. While there are lots of different kinds of optical modulators, at Intel we are specifically focusing on silicon-based micro-ring modulators, which I think some of you may be familiar with. In a micro-ring modulator, you've got light traveling on a straight waveguide, and it gets coupled onto a circular waveguide. Because it adds back with a phase shift, you get this wavelength selective transmission curve. Now we dope the circular waveguide as a PN junction, and when you change its bias, you change the carrier density in the depletion region, which changes the refractive index of light as it passes through it, which means that you can use this bias voltage modulation to change the phase shift of light and then change the transmission curve, change the position of the resonance wavelength. So if you had a laser at some wavelength, because you're changing the insertion loss at that lambda in, you're actually introducing intensity modulation on that light. This resonant nature of the ring makes this bias-induced phase modulation particularly effective. And so you can use much smaller driver swings than you would need in other modulators. For example, there's a very popular one called Mach-Zehnder modulator, where the driver swings need to be much higher to achieve this appreciable intensity modulation. So this lower swing can potentially be very compatible with CMOS. In fact, we actually further optimize this phase modulation efficiency by optimizing doping, etc. But those are things that are beyond the scope of my talk, and I'd refer you to some papers later on for that. Now, the compact nature and the resonant behavior of the ring also makes it very thermally sensitive. And this is actually a big bottleneck. This has been a big bottleneck traditionally in the adoption of MRMs in optical transceivers. What we do is we dope a portion of the ring as a resistive heater so that we can control the local temperature and bring the resonance back to where we want it to be, to the desired position. And many groups, including ours, have recently shown CMOS-based thermal control circuits that are continuously operating. That is, they are not. You don't have to take the ring offline to stabilize it. They're in the background. They're always working, and this can help maintain the ring's performance and make sure that the resonance wavelength is where you want it to be. Overall, this modulator is really compact compared to the Mach-Zehnder modulator. There is a 150x size reduction. And because it is so compact, any diode capacitance associated with the modulator is also small, and you can get really good modulator bandwidths. So we talked about low driver swings and high modulator bandwidths, right? So this is, I've taken a snapshot of, our latest MRMs. So we've got a 10 micron ring, which has a bandwidth of about 50 gigahertz. And with this modulator, we were able to get an open eye at 120 gigabits per second with PAM4 modulation, and this was without any scope equalization. And it had a very decent swing of with a very decent swing of 2.5 volt peak to peak, which you can easily achieve in CMOS, perhaps with a little bit of work. The second modulator, this latest modulator, is a 4 micron ring, and its bandwidth is about 60 gigahertz at a very decent reverse bias of 2 volts. And in fact, now we've transitioned to using these metal heaters instead of a P-silicon heater. So this allows us to dope more of the junction for phase modulation. And because the metal heater has a low resistance, the voltages required to control this heater are also more CMOS compatible. Finally, with this modulator, we were able to show a 224 gigabits per second PAM4 eye. This eye is with equalization, but overall what this is intended to show is that MRMs are very suitable for high-speed optical links. The next thing I'll talk about is the options for laser sources for optical links. You can have either an external laser or an internal laser. If you have an external laser, it's very thermally stable because it's not exposed to a lot of thermal variations that happen inside transceivers. Now, because it is external, you can also split the fiber to multiple transceivers. This is actually really useful for coherent links, where you may want to forward the laser to avoid the overhead of optical carrier recovery. The challenge with using an external laser is you have a lot of coupling loss every time you couple to the transceiver. The fiber alignment itself is costly. And because you are splitting the power between multiple transceivers, the actual power into a transceiver may be low, and you may need amplification to complete your link budget. We at Intel use integrated lasers quite a bit. In this case, a 3-5 wafer is actually wafer bonded onto silicon uninsulated gratings on a silicon wafer. And because you're wafer bonding, the light couples directly into the silicon waveguide. And so you have very low coupling loss. You don't have very costly fiber alignment because you're wafer bonding. And so much light couples that you may not even need amplification to complete your link budget. The challenge with the integrated laser, of course, is because it is integrated with the transceiver, you're going to see very harsh thermal environments. And it's really important to develop both package techniques and also circuit techniques to help manage the laser performance. So now some highlights of our laser. These are actually published in the photonic engine paper that SPPD did in OFC 2020. So the photonic engine, as I mentioned, is a 1.6 terabits per second optical I/O module. And it has 16 channels at 100 gigabits per second, and each channel has 2 lasers. The reason for the second laser is it's actually redundant. If the first laser dies, we can use this LCI switch to kick in the other laser. Now, the second laser, being identical to the first, requires no additional patterning steps in the 3.5 process, so it actually comes at no additional cost. So this is like a benefit of the integrated laser. It can be high volume and very low cost. It can also, as I mentioned, provide a lot of power, even at high temperatures. So this is a measurement of the power versus bias current of our laser at 80 degrees Celsius. You could easily get 20 milliwatts at 100 milliamperes. Now, earlier this year, we presented a 32 gigabits per second NRZ link, which needed only about 2.5 milliwatts of power from the laser to hit a BER of 10 to the power minus 12. So this laser could easily supply many such links. Now, 2 other metrics that you care about when you talk about integrated lasers in the IMDD scenario is the side mode suppression ratio, right? These are spurious tones in the laser spectrum, and you want them to be low compared to the desired carrier. So in our case, the side mode suppression ratio was better than 55 dB for all pairs of lasers across 16 channels. The other metric that you care about is relative intensity noise. So this is described in dB per hertz, and it's relative to the carrier power itself. And this is important because any amplitude noise in the laser directly contributes to eye closure. So this is better than minus 150 dB per hertz measured across all 16 channels. All right, so now the last component that I want to talk to you about today is the photodetector. As you mentioned, the photodetector converts the incoming light into a photocurrent, and the gain with which it does so is known as the responsivity. Now, many of you may know this general concept that in any receiver, if you front load the gain, then you can immunize yourself to the noise of the subsequent stages, right? So you want the responsivity to be high to have good sensitivity in your receiver. The second thing that you care about is the input bandwidth. Any diode capacitance you have from the photodetector, any pad capacitance, any electrical capacitance will all add up at the input node and limit your bandwidth. So actually in all of our work, we've used the shunt feedback TIA, which is like very common. Anyone in optics knows this. It allows you to get a high gain through that resistor, and it also attenuates the input impedance by the gain of the amplifier. So you can actually improve the bandwidth at that node quite a bit, and that's how you desensitize yourself to the photodetector cap. The third thing we care about is any dark current or short noise in the photodiode, because these are adding directly at the signal input itself, right? So they will directly affect your sensitivity. We are using germanium photodiodes. These germanium photodiodes are developed by growing germanium on the silicon waveguide. And these actually get a very appreciable responsivity of like an ampere per watt almost at a very moderate reverse bias of 1 volt. Again, these all have to be generated in CMOS, hence the emphasis on voltages. And you can get very high speeds out of them, like in the order of 30 to 40 gigahertz. So this actually brings to a close the section on the photonic device, everything I wanted to say about photonic devices today. So we talked about our integrated laser source. We talked about these compact ring modulators that are CMOS compatible. We talked about a high bandwidth and high responsivity photodiode. So I can stop here for like a couple of minutes of questions, but I would say that if you have a longer question, let's leave it for the end of the talk. But because this talk is going to move between many different topics, let's just stop here for like maybe a couple of minutes, and if anyone has a question, yeah, please go ahead.
Any plans for WDM?
Later in the talk, yeah. Yeah.
So one thing you told us is that you are using a ring resonator with a bandwidth of around 54 gigahertz, right?
50, yeah. Yeah, it is.
Yeah. So in case of Silicon-Photonics, when we are using a PN junction and all, this is the maximum capacity which can achieve as per the research topics, right?
Okay.
So are there any plans to move further to different platforms or something?
Well, I mean, we're optimizing the doping and also looking at different kinds of junction topologies.
Correct.
And right now, for the bandwidths that we are, sorry, I really wish that I didn't want to do it. Right. So this is our latest swing modulator. Right. This one is even smaller. This is 4 micron. And actually, the RC capacitance is not so much limiting as it is the electro-optic transition, the electro-optic transit time bandwidth, right? And 60 gigahertz is more than enough for some of the data rates that we are targeting right now. But yes, we are exploring different kinds of junction topologies as well as optimizing doping to push this bandwidth. But there might be a physical limit.
Yeah. That is basically a physical limit because of both the electro-optic transition and plus junction capacitance which appears due to the
right. Yeah.
So how much you optimize it and how much you do it, there is a very small.
Yeah. But this in itself, even if your Nyquist was 60, this would enable 120 gigabits per second NRZ link.
Yeah.
So that and the plan is to do WDM and also, bring together a lot of arrays. This is what WDM is. So that, I mean, I don't think we've hit that limit yet.
Because there are other which shows bandwidth of more than one.
True. I think I mean that we can have this discussion offline, but CMOS compatibility and silicon photonics is an important factor in cost and high volume manufacturing. So that's sort of why we are focusing on silicon-based dynamics. They're also really compact. So WDM is a lot easier because you can have a lot of areas which are very compact.
Compactness depends upon the property.
Yeah.
So what are the materials you are using on that? Based on that, you can increase or decrease.
Right. Okay.
Finally,
Yeah.
will you be covering coherent in this talk?
No. Go ahead. Okay. Right. Okay, so now I'm going to talk about some of the companion electronics that we developed for these single lambda links. All right. So let's talk about the high-speed driver that we need to drive the optical modulator. So, I mean, we just talked about how MRMs place in intensity modulation. Essentially, you move the wavelength selective transmission curve between 2 points and you change the insertion loss at the lambda end. And that's how you introduce the intensity modulation. How far you move the curve depends on how large a voltage swing you're applying. So the larger the voltage swing, the larger the optical modulation amplitude or the eye opening. And as I mentioned, what we want is that swing to be compatible with CMOS drivers, right? Now, if you wanted to place more complex intensity modulations in order to increase the data rate per lambda, you could do, for example, PAM4, but that requires an even higher swing so that all your 3 eyes are open. And you could easily, for example, have a situation where you need to generate more than 2 volts for CMOS. Now, that isn't particularly simple. I'm not going to go a lot into circuit details. I'm just presenting a snapshot here, but we can talk about it offline if you want, and in the question section. We've got stacked CMOS drivers, and then we're also using, for example, here differential swings to generate, something. I think this is of the order of 2.5 volts peak to peak. The other challenge with using microring modulators is the optical nonlinearity that they introduce. So because the shape is a Lorentzian, you actually end up introducing static level mismatch, right? And then you also have dynamic nonlinearity. The modulator's bandwidth changes based on the insertion loss or the detuning of the resonance from the laser. So this actually introduces transition-dependent ISI. We talked about ISI earlier today, but this is transition-dependent ISI. Depends on whether you're going from a high level to a low level or a low level to a high level. Dynamic nonlinearity is a bigger problem. So what we do is we introduce pre-distortion for the for the static nonlinearity. And then we introduce a nonlinear FFE, which basically applies the FFE coefficients change based on which transition you're doing. And that helps us compensate for dynamic nonlinearity. So using all these concepts, we implemented this single lambda 112 gigabits per second PAM4 transceiver. This was implemented in 28 nanometer CMOS. And this was flip chipped onto a PIC or a photonics IC, which contained the integrated laser and the optical modulator. We've also got thermal control on here for the microring modulator, but I'm going to talk about that in another section. So that thermal control helps us to maintain a constant detuning from the input laser wavelength. By detuning, I mean the position of the resonance with respect to the input laser. This is what I'm talking about. So you can maintain a constant insertion loss in the link. So this is a measurement of the optical eye at 112 gigabits per second. And I'm trying to show here the advantage of using nonlinear FFE. This metric TDEQ. It's a PAM4 specific metric. It stands for transmitter dispersion and eye closure quaternary. Essentially, what it means is the amount. It's a ratio of the amount of noise that you would add to an eye from an ideal transmitter in order to get the same symbol error rate as you would from your own transmitter. So if this number is higher, it means you've got a poorer transmitter, and we typically like to keep this below 2 dB. So when we didn't have the dynamic nonlinearity compensation enabled, we had a TDEQ of 2.8, and when we did enable it, the TDEQ improved vastly. So the next thing that I'll talk about is the companion receiver that we built for this optical transmitter. This is the same shunt feedback TIA topology that I talked about briefly. You've got photocurrent coming into it, and the job of the TIA is to electrically amplify it. Following the TIA is a single to differential converter, followed by a few stages of gain peaking, right? You saw this in the earlier talk. Now, we want to improve the receiver sensitivity. So we want to reduce the input referred noise. One very simple way to do that would be to reduce the bandwidth over which you're integrating noise. And you could do that by lowering the bandwidth of the front end. And if you have a very high gain in the front end, then you also are insensitive to noise in the subsequent stages. That's what we talked about. That's what noise figure, you may be familiar with those topics from wireless as well. So in this case, we actually measured a breakout, and this had a bandwidth of about 25 gigahertz, a gain of 68 dBohm, and an input referred noise of only 2.5 microampere RMS. The problem with attenuating the bandwidth of the front end is you're going to introduce a lot of ISI, right? So here's an eye that was measured from this front end at 53 gigabits per second. The NRZ eye is open, no equalization needed. But the PAM4 eye at 106 gigabits per second, this was only open with scope equalization. Now, you can actually implement that equalization on chip, right? So we implemented a mixed signal equalizer, and this had 2 taps of DFE and 1 tap of FFE, and we optimized we did some optimizations to determine how much equalization we wanted. The FFE was needed in order to equalize the precursor. So we implemented this receiver in 28 nanometer CMOS, and this was actually measured by wire bonding it to a 3.5 PD, which had a bandwidth of about 35 gigahertz. And the BER that was measured was about this is a prefect BER of 2E minus 4. And this is sufficient for the Ethernet standards. And this achieved an energy efficiency of about 3.9 picojoule per bit and minus 8.3 dBm sensitivity. Essentially, the important thing about this work was this was the first time that anyone ever integrated the high-speed receiver and the mixed signal equalizer in CMOS on the same chip. So we actually did a multi-channel version of the optical transceiver. So there are 4 optical transceivers, each capable of 112 gigabits per second PAM4. But we've also implemented another one, which is an 8-channel 50 gigabits per second NRZ, and I've got the pictures of both the prototypes in here. They're about ISO data rate, implemented in the same technology, about ISO area, but the NRZ doesn't require all of this complex equalization that the PAM4 does, because PAM4 is much more sensitive to residual ISI than NRZ. So because you don't need those complex equalization techniques, the NRZ transmitter can be a lot more energy efficient. And you don't need FEC to achieve the BER target of 10 power minus 12, which makes NRZ particularly attractive for these low latency, high energy efficiency interconnects that you need in compute applications. So while PAM4 is very suitable for Ethernet, we are currently looking at this for compute interconnect. So here's a picture of the NRZ transmitter. Because you need a lot lower swing for the NRZ than PAM4, you don't have to do a differential stack driver. It's sufficient to do a single-ended stack driver. And because you don't have to do complex equalization, you don't have to route high-speed signal and data over many slices. And that's definitely a power advantage. And because the transmitter is so compact, you can do this very efficient serialization in just one stage. And so with all of these transmitter architecture updates, we were able to get an energy efficiency of just 1.2 picojoule per bit at 50 gigabits per second. And here's its companion receiver. It's very similar to the PAM4 receiver. So you've got modulated light coming in, which is absorbed by a microring resonator on the RX side, right? And so you want its peak to be aligned to the why do we have a ring in a single lambda link? Not really, this is part of the WDM picture. We'll talk about that in a second. So the Dmax is aligned to the optical carrier so that you absorb most of it, and then the drop port light is incident on the photodetector, which then supplies the AFE. Now the AFE is similar in as in PAM4, we make it low bandwidth so as to improve the noise, and then compensate with some mixed-signal equalization to recover the bandwidth. And we use DFE because I don't know if this was mentioned in the last talk, but DFE is a cool way of recovering bandwidth without enhancing noise. So we implement DFE, and actually we implemented it with loop unrolling so as to be able to meet the close the loop at these really high data rates. So now this actually brings to a conclusion all the CMOS electronics I wanted to talk about today. So we talked about 100 gigabits per second PAM4 link, and basically the challenges that are that CMOS has in providing the swing, and we talked about techniques of nonlinearity compensation that would help us develop CMOS drivers for PAM4 with ring modulators. We also talked about the companion electronics and some techniques to enhance sensitivity and combine mixed signal equalization into the mix. Then we talked about this more energy efficient and latency friendly 50 gigabits per second NRZ link. And yeah, I think before we move on to WDM, let's stop here again for like a couple of minutes, take a few questions, but reserve the longer questions for the end. Yes, please.
Could you please show the efficiency of PAM4 versus NRZ?
Yes. Yeah, here you go. So you can see the receiver is not that much better. It's because when you use loop unrolling, for those of you familiar with loop unrolling, you end up having two samplers, and then you have one DLEF sampler, which you end up having three samplers per slice anyway, as you do in PAM4. So that's one of the nuances there. But
So you're using IQ modulation technique for PAM4?
no, we're just doing intensity modulation. So we have two different driver swing levels on differential.
Because generally in optics we use IQ. The one issue so that we go wrong.
Right.
So that's what.
Yeah, in this case, we're just using intensity modulated, like just directly connect. Yeah.
But the energy efficiency, the biggest switch to PAM4 is coming on the transmit side. So, I mean, what's the issue?
It's the nonlinear FFE. So you end up needing, in order to have good resolution and good range, you end up needing a lot of slices. And so you can imagine in layout, you've got this big thing sitting over there, and now you've got to route very high speed signal to all of it. And you depending on how you want to route things, you may have to do multiple stages of serialization. Every serializer costs a lot of power. So overall, the more equalization we began the talk with saying, when you have to do SerDes with a lot of equalization, it can become quite a significant portion of the package power. So that's exactly what you're seeing here.
Can you tell the constellations to prevent any such transitions which will cause higher ISI levels? Because the levels is the ISI, the amount of ISI is dependent on the previous.
So that would be some sort of coding,
yes,
which would introduce further latency, right? Because you're saying, if I want to cull transitions, I'm actually getting rid of information, right? So you have to encode that information in some other manner. And encoding would cause, I think that was sort of your question earlier. Yeah. Would basically increase latency. I mean, you could do that, it would increase latency, as is we are meeting only a prefect BER of 1E minus 4, which means you're already doing forward error correction if you want to hit higher BER. Yeah.
Let's say, consider that is a weaker net. Right now also we have some SerDes link which is getting converted to some light kind of a medium that goes by OFC, optical fiber cable. So like what I see is you are introducing the ring modulator, which is changing the thing that there is a modulation in OFC also.
Yeah.
So can you compare this with the conventional system right now?
Oh yeah. So we had that slide at the beginning of the talk. So these are our more conventional products for Ethernet. Oh, we lost the slideshow. Sorry about that. Oh, it'll just pop up on Teams then. Okay. Yeah, keep it that way so I can find the slide again. Yeah. Okay, so we talked about that earlier in the presentation. So
in this case, the modulation, the encoding is taken care by the SerDes itself. The encoding is taken care by the SerDes itself here.
Yes.
So here, in that case, the optical medium is just transferring that
Yes.
0 or 1 directly.
Yes. Yeah. And in the other one, also that is the case. So ultimately, in the link, somewhere you're going to have to decode, right? So overall, you're going to have latency if you encode, which is sort of what this question is. Okay. So how do we go back? Okay. All right. So this is where we were last. Okay, this is where we were last. All right, so let's move on to WDM, your question. So wavelength division multiplexing, right? So we talked about these PAM4 links, which help us increase the per lambda data rate by doing multi-level intensity modulation. So now we're going to talk about a way to increase per fiber bandwidth through a multi-lambda approach. Okay. Yeah. So in WDM or wavelength division multiplexing, you've got light which is composed of multiple wavelengths, and you can place an independent data stream on all of them by using a dedicated driver. Finally, you'll combine all these modulated light and pack them onto a single fiber, dramatically increasing the per fiber bandwidth at what is ISO power efficiency. So there's two challenges in the optical puzzle. There are two missing pieces in the optical puzzle before we can actually complete this WDM system. One is getting a multi-wavelength laser source in the O band. These are not that common. There are lots of them in the C band. There aren't that many in the O band. So actually, a lot of people measure with tunable sources, right? So you can only show one channel at a time in a WDM system. So we finally got hold internally, because we made it, a multi-wavelength laser source in the O band. And then the second puzzle is. The second piece in the puzzle is how do you make sure that you only absorb one of those carriers per channel? So how do you demultiplex this WDM source and ensure that only one is going to, a dedicated optical modulator? So we've manufactured this, recently, not manufactured, we prototyped this multi-wavelength laser for all our WDM applications. So it's an 8 lambda, it's an 8 element DFB array where the wavelength carriers are spaced by about 200 gigahertz, and they've only got about a 10% error in that spacing. And the reason we can get such tight tolerance is because we do 3-5 wafer bonding onto silicon, and you can leverage CMOS lithography in silicon to get these really high resolution gradings. The second nice thing about this is because the wavelengths are so narrowly spaced, you can use a single 3-5 epitaxial structure, which you would not be able to do, for example, in CWDM, where wavelengths are spaced by like 20 nanometer. This is only 1 nanometer. And because you only need a single structure, this really simplifies the fabrication process and also reduces cost. So this got some traction, and you can see here some news articles where it was talked about. So because this laser is integrated, as we talked about before, this is going to be exposed to some very harsh operating conditions. The temperatures are going to run very high. So we measured its performance across temperature. You can see that the absolute laser wavelength for all the 8 elements, all the 8 elements changes with temperature, right? But the delta lambda between them remains constant at 200 gigahertz, which is really what you need. And then the second thing is power. You can see that the power again varies with temperature, but the variation between the tones remains to within 1 dB. The second thing that I wanted to talk about was the wavelength demultiplexer, which ensures that the WDM source is demultiplexed such that only one carrier is absorbed per channel. Now, the ring resonator, being a resonator, is actually very naturally fit for enabling this kind of wavelength multiplexing, demultiplexing. That's actually another advantage it can have over other optical modulators. So we use this tunable heater to place the resonance spectrum, to shift the resonance spectrum such that only one carrier lies in its resonance spectrum. And that's how you can naturally enable WDM. Each light will be absorbed by just one resonator, modulated by its corresponding transmitter, and then sent out. And you can pack in multiple wavelengths into the ring's FSR. So for this 8 lambda case, we've packed in these 8 lasers at 200 gigahertz into the 11.5 nanometer FSR of our 4 micron ring. So I'm going to just talk very briefly about a couple of challenges associated with doing WDM with MRMs. The first is crosstalk. Well, that's going to happen anywhere, but essentially crosstalk is the interference between modulated carriers, and it limits the spacing. So it limits how many wavelengths you can pack into the FSR. The ring quality factor is an obvious metric because it controls the sharpness of the transmission spectrum. So it's an obvious metric for how well you can isolate the different carriers. But there's a more nuanced metric, there's a more nuanced phenomenon which comes from the photodiode nonlinearity. So we've talked about these two things in this recent publication. I'm not going to go into the details of that today, but I am going to talk about another concept called super FSR very briefly. So if crosstalk is limiting your wavelength spacing to some delta lambda, it means you can only pack in something like FSR by delta lambda number of wavelengths, right? So how do you improve that? So there is this concept that has been developed. I mean, people know about this, it's called super FSR. I'll talk about it really briefly. So let's say you've got these carriers which are spaced at delta lambda by 2. This is half the spacing that would be allowed by crosstalk. So what you can do is you can split it into odd and even carriers, right? And then you can have this bus where all the lasers are spaced by what you need for crosstalk, and you can modulate all of them and combine them back. And so you've managed to pack in twice the number of wavelengths than crosstalk would have allowed you to. In fact, you can do this even more aggressively, and people have. They've packed in 64 carriers into the FSR, and this is this paper from Columbia, which I'll point you to if you want to learn more about this concept. The second challenge that I'll talk at length about is developing scalable thermal control. So rings are super thermally sensitive. We all know that. We've talked about, I've said to you that no, a lot of people have developed these CMOS circuits that can control the ring's temperature. But what I'm also going to show you is that many of these techniques don't scale very well with WDM, especially if you have heterogeneous integration. So if the two things, the EIC and the PIC, are on separate dies, scalable thermal control is actually harder to develop. And so I'll talk about a technique on how we do that. So once again, just going to revisit the concept of thermal sensitivity for people not very familiar with it. So we know rings are thermally sensitive. We've included a heater on chip so that we can actually move the transmission. We can control the local temperature and move the transmission spectrum to where we want it to. And so if you had process variations or geometry variations, you could do this statically. You could take the ring offline once and just calibrate it. But more importantly, if you have temperature variations, then you need to do this continuously. And that's the purpose of the TCU, which provides feedback to the ring heater to continuously control it. So you never have to take it offline and basically bring your optical transceiver offline to calibrate the ring. Now, basically to motivate why there is a problem with building scalable thermal control, let's see what it takes to build just one. So we need a way to sense the ring's lock point in order to know where its resonance is. So one way of sensing the lock point would be, for example, to measure the average insertion loss at the input laser. So you could do this by measuring the average absorbed power of the ring. So if there was any variation in that absorbed power, you know that the ring is moving, right? You could sense the insertion loss by basically putting in two monitor PDs. You tap off the input, tap off a fraction of the input power, and you know what the input power is. You've got a measure of the input power. You tap off through-port power, and you take the ratio to measure the insertion loss. But what you've done in this process is you've added two extra paths. So now you can see what's going to happen. If you try to do WDM with a technique like this, you'll have to add two interfaces per ring, right? So if you needed N channels, you'd have two N extra interfaces over what you would need for the diode plus the heater anyway. So our observation that helped us get around this was the fact that the ring is a PN junction. It's a photodiode. It's going to generate a photocurrent in response to the absorbed power. So we can just use that as a measure of the lock point, right? And so this is a ring. This is the ring's absorption curve. It's the inverse of the transmission curve. And typically you only bias in the red bias region, which means that the laser wavelength is always lower than the ring resonance. We can talk about this later, but this is a stability issue. You never want to bias the ring in the blue bias. So if you know that you're always going to bias in this left half, every photocurrent corresponds to a unique insertion loss. And so this is how you can use this information from the MRM photocurrent to determine the insertion loss and lock it to a desired point. And basically, you're reusing these two paths. You're using the bias and modulation path, and anyway, you have to have one heater path. So you really have no additional paths anymore for this hybrid interface. So the output from the photocurrent sensor will go to the TCU. You'll program in a desired insertion loss, and then you'll basically correct the heater, right? And you build this loop around each of the rings. And you have no additional interfaces because you basically leverage the ring's own photocurrent. So this was the big thing about developing TX-TCU control transmitter transmitter thermal control. But really, in an optical receiver, you will have to control not just these rings, but also the receiver side rings, right? So let me just talk about this architecture for a second. So you've got the light coming out of the laser. You modulated it individually. Each of them has an independent data stream. You've combined them all. You've sent them on a fiber to the receiver side. And at the receiver, the ring is performing, again, the same function. It's taking the modulated optical carrier and sending it to its dedicated receiver, right? So this is a demultiplexer. And you need to make sure that this ring is aligned to the laser that it needs to absorb. So how do we develop a thermal control for that? Okay, so this is the picture we saw before. This is the receiver, the electrical receiver. You see the shunt feedback TIA. It's getting its input from this germanium PD, which is getting its input from the drop port of the ring, right? So if you want to maximize the input current, like input current, like I said, you need to maximize the optical power. That's the ring peak needs to be aligned with the laser. Now, a measure of the absorbed power is actually the average current that is received by this photodetector, right? Similar to the MRM. And you can send that as an input to your thermal control unit. Unlike the DXTCU, you have no reference here because you have no idea how much power is going to come into your optical receiver, right? So you have no a priori knowledge. So we had to come up with a different algorithm. And the one we use is the slope minimization approach, right? If your laser was located to the left of the ring, then you get a negative slope, right? And how do we measure the slope? We slightly vary the power that we would anyway apply to the ring heater, right? And we detect the change, the delta in the photocurrent. So if you increase the heat, the photocurrent becomes lower. If you decrease the heat, the photocurrent becomes higher and you measure a negative slope. On the opposite side, you would measure a positive slope, right? And then at the peak, you would measure zero slope, right? So that's the algorithm we use on the RX side, different, a little bit different from the DX side. But they're still using the photocurrent. So again, no additional interfaces between the two hybrid dies. So this is a circuit implementation. So all we are doing is we've got the receive signal strength indicator, which is basically average current from the photodetector, which is we scale it, we digitize it, we send it to the digital backend, which does the slope estimation, and then we actually compare it to the desired slope. Now, yes, to lock in the peak, you'd want a slope of 0, but in many cases, we actually also lock off peak just for stability. And so you can program in the slope over here because of this, you have all these options. You average the error, and then you use a sigma delta modulator to basically convert this 14-bit code to a 4-bit code that controls an IDAP. Now, we actually compress the current before sending it into the heater, and this is just a bookkeeping thing. We want the power over here to be linearly proportional to the code that's coming in. So that's the only purpose of the square root circuit. So all of these things I described, the transmitter, the receiver, the thermal controls, we've implemented them in this 8-channel 50 gigabits per second NRZ, 50 gigabits per second per lambda NRZ optical transceiver. So it was fabricated, the electronics was fabricated in 28 nanometer CMOS, and we flip chipped onto the PIC. The PIC contains the laser array and all the rings, everything that's needed for DWDM essentially. And then we take this package and we wire bond it to a carrier board so that we can interface with external equipment and measure our life's work. So here's the measurement setup. So we get a half rate clock from an RF source, and this actually provides the clock for our transceivers, all our transceivers. We've got the 8 lambda laser in, that's providing all the 8 carriers. In the first case, this is passing through all the TX rings, and we're placing independent modulations on them. And we've got this optical switch which allows us to either send them back to the receiver, so it's like a loop back measurement, right? Or you can send them out to the chip. So this way, if you send them out to the chip, you can look at the TX output eyes. By the way our pattern generators are on chip. They're capable of PRBS 7, 31, 11, PRBS 7, 15, and 31. And we can basically seed them differently. So we know that they're not interfering with each other. So these are the 8 optical eyes, right? We can get an extinction ratio of better than 5 dB in all channels. So this is actually the first demonstration of such a high data rate in WDM, with all of this integration.
1.2 nanometer difference?
1.2 nanometers. And then we switched the switch back into loopback mode and sent it into all of the receivers. So here's first the measurement of a single lambda link. This is measured at 32 gigabits per second. We're climbing up to 50. The chip is in the lab, just measuring. So we can achieve a bit error rate of 10 power minus 12 with a sensitivity of minus 10 dBm. Then we turned on all 8 lasers, and these are the bathtub plots for all 8 channels. And you can get 10 to the power minus 12, but we're seeing a 2 dB degradation in the sensitivity per channel, and we're trying to debug that. I can conjecture, but I won't. But yeah, work in progress. But this is also actually one of the highest data rates that has been presented in such a highly integrated link for DWDM.
Quick question.
Yeah.
Only 2 out of the 8 have a narrower backup.
Yes.
All 6 are wide.
Yes.
Specific reason for that?
There are a whole bunch of things that we're investigating. Yes.
Published? Not published.
These eyes are published, but the
The
debugging,
reasons for that.
the reasons for that.
They could publish it.
We stated this note.
Which one?
28.
28 nanometer. Yeah. Yeah. CMOS is 28 nanometer. The photonics is in our in-house foundry, the Silicon-Photonics foundry.
So 28 nanometer will be data.
Yes.
So most of people.
It's a MOS. I mean, it's a, is it a filter? I don't know if it's a
28
filter. This is TSMC 28 nanometer. It's not a filter.
Is it the huge HPC process or HPC plus?
This is actually the other one, I think. I can get back to you on that. Yeah. I don't recall.
Okay, ma'am, so this particular 32 gigabit per second link, it can scale up to 55 because you mentioned 50.
It is designed for 50. It is designed for 50.
Okay,
Yeah.
but it has the potential for 50 if debugging.
Yes.
Very conditions, sometimes conditions, right? Can't say. Yeah.
Yes.
It has the capacity.
Yes. As soon as it is done, we'll definitely publish it.
Then wait for it.
Yeah.
Because,
Okay.
DWDM is the killer feature for these small links.
Yeah.
Where did you lose out from 50 to 32?
So we're just bringing up the link in parts. Yeah. Yeah. We don't bring it up at 50 the moment it comes to the lab. It's too scary.
I have this. So you have both transmitter and receiver
Yes.
side. You have used a feedback loop
Yeah.
to
Let's,
basically
yeah.
control the heater, right?
Yes.
And, so how much latency does that feedback loop add, or doesn't add?
it is completely orthogonal to data. Yeah.
Right?
It's a completely different.
It won't affect the I parameter.
It has to have enough bandwidth, so you'll have thermal variations, and the TCU has a certain bandwidth. It's a feedback loop, has a certain bandwidth. As long as it is able to keep up with the thermal variations, your insertion loss should remain constant. And if it is not doing that, that would show up in something like the optical eye. You'd see eye closure, right? Because your insertion loss is changing, so your OMA is changing, and you would see the eye doing different stuff. Yeah.
Will it only affect the eye closure or the periphery of the eye? Will it widen that, like for the eye? Will it also widen it, or it will only affect the closing of the eye?
I know it will affect the OMA. Whether it would affect, I mean, so obviously the conventional wisdom is this is just jitter, right, from both clock and transmitter. Difficult for me to say. I'd have to think about it and get back to you. Sorry. Yeah.
It might, because of that, it might result in.
I mean, I know that it will change deterministic jitter because your eye height is now different. So deterministic jitter, which is from ISI, will change, right? But I don't know if it would affect like statistical jitter, the timing induced thing.
But if that was the case, then
I can think about it and get back to you. By the way, sorry, could you repeat?
If that would be the case, then there would be a very large cyclical change in the eye measurement, right? Because if it is
Yes, it was so exactly. So if it was a very low frequency effect, right, and your TCU bandwidth was just so low that you couldn't even capture low frequency effects, then yes, whatever the bandwidth of that, whatever the frequency of that variation is, you would see the eye changing over that period of time. But you'd have to have a really bad TCU for that. Yeah. So yeah, I mean, we have not characterized exactly what thermal variations you see in package, right? All I can say is that the TCU that we have is capable of meeting what we have in the lab right now in this package, right, which is all flip chipped and put onto a carrier board. And why do we know that? Because we can measure a PRBS. So this is with the PRBS 15i, but we've done this measurement with the PRBS 31i. And so over that time period, we know our TCU is able to keep up with whatever thermal variations. All right, so actually I did very well on time. So, yeah.
So can you please go back to slide number 89 and I am looking to get more explanations out of that. Slide number 89.
Do you mind if we finish the talk and come back to slide number 89?
Sorry.
Yeah, mostly because I have to go up and down in the slides and it makes me lose my place. Okay, sorry. So we've talked about these multi-level modulations to improve per lambda bandwidth. We've talked about WDM to improve, per fiber bandwidth. And another thing that's not exactly a low-hanging fruit, but a desirable fruit is polarization multiplexing. And we've shown this benchtop experiment, a couple of years back. Essentially, you can encode information in both polarizations of the light and effectively double the data rate that you have per lambda. So we've shown 400 gigabits per second, in the OTX, and that means we have a path to 1 terabits per second for fiber. But it's a long story still.
Getting the wavelengths for the vertical polarization on the same process.
So this is a difficult question for me to answer because I'm not a photonics person. All I can tell you is that all the components that are required for these, like the deep, I believe there's a polarization beam combiner and then a polarization splitter and rotator. I think the PT is your phase tuner. So I believe all of these components have already been developed in Silicon-Photonics. So exactly what the physics behind it is, like I said, the disclaimer at the beginning of the talk, I couldn't tell you about the physics. All right, so the last very important research vector in co-packaged optics is packaging, because that's not simple. So I talked about this 1.6 terabits per second photonic engine, right, which is an optical I/O module. And it consists, as I mentioned, integrated PIC with the laser and the optical modulator, and it's co-packaged with these SerDes ICs that are off the shelf. So this was done a couple of years back. This paper from ATTD, our assembly and test department, talks about all the pain they had to go through to package this, right? So the first problem that they solved was how do you get a low loss link between the switch and the photonic engine. So there's this special technology, the patch and interposer technology, which is for high density interconnects that was leveraged to. But basically, the idea is that getting the data from the XPU to the OCI tile or the XPU to the photonic engine, this is also a challenging problem because you still have that short SerDes that you still need to. So you need that to be low loss, and that's where packaging comes in. That's a challenge of packaging. The second is thermal management. So this is actually the organic substrate on which the Silicon-Photonics ICs are present. They're on the top, and the lower power management ICs were at the back. And so this heat spreader was placed on top of the photonic engine to manage the heat. So thermal management in package is an important problem. I'm not talking specifically about the solutions as much as telling you that these are the issues of packaging. Got to develop this this high speed, low power, short link, electrical link, and have to be able to manage the thermal power. More importantly, and this step comes at the end, which means you can actually lose a lot of good dies, is fiber attach. Because everything can work and then your fiber alignment goes awry and you lose a perfectly good die. So the way fiber attach was done in this photonic engine was CMOS lithography, and you can use CMOS lithography in this deep etching to put a V groove, which can help you with passive alignment, right? So this overhanging portion of the die has a V groove, which we used for passive fiber alignment. I believe the coupling loss was about 1.2 dB or something, and that's about 0.6 dB more than what you would get with active alignment. But active alignment is a more costly process. But overall, the take-home message is that packaging, assembly, and test are actually a disproportionate amount of the total cost of the product. And what we need to do is develop low-cost, high-yield packaging, especially for things like fiber alignment, which come at the end, to make sure that co-packaged optics based on Silicon-Photonics is actually this wide-scale adoption completely depends on coming up with solutions for these packaging problems. So I'm going to go to the conclusion and then we can take questions. So what did I talk about today? I talked about intensity modulated links, right? I spoke to you about Intel's technology, our integrated lasers, modulators, detectors that we've developed to enable these links. I talked about what it takes for CMOS to actually, drive this silicon photonics platform. We talked about some of the challenges with these, multi-level intensity modulations. How do you get a high swing? How do you compensate for optical nonlinearity? But I also talked about very energy efficient and low latency NRZ links, which do away with some of these problems. We talked about wavelength division multiplexing, our multi-wavelength integrated laser source. And then we talked about some of our 8-channel arrays and I guess we didn't talk about the 4-channel arrays today. We showed the 400 gigabits per second optical transmitter, the work in progress 32 gigabits per second NRZ transmitter. We talked about the issues with using MRMs for WDM, right? And one of the challenges was scalable thermal control. We talked about potential solutions for that. Polarization multiplexing is one possible future research vector that we've, been dabbling in. And finally, the packaging challenges for CPO that need to be addressed if this has to become a thing, right? So, okay, so that actually does complete the talk. And made it. I made it.
What tool do you use?
Yeah.
What is used for guidance?
Visio.
Visio.
Yes. And actually, MS Paint.
Paint.
Yes. It's a very useful tool if you know how to use it.
Could you specifically tell what did you do in Paint? Because a lot of people might get benefit.
Have patience and know that pixels are very useful. Zoom in a lot. Yeah. It just helps to edit a figure if you've already put in all the effort to make it in Visio and you need to make small modifications. It can be very painful to keep going back to Visio and snap, Yeah, so.
Because all are vector graphics on Visio. Or they are JPG.
Oh, these are, I actually screenshot the image. Yeah, I turn off the grid and I screenshot the image. Okay, sorry, you had a question.
Yeah, can you please go back to your slide number 89?
Yeah. Oh, we may lose the presentation though. Sorry, I need to represent the screen somehow. There we go. I got it. Yeah.
Yeah. So here I'm seeing some photo detector, thereafter distribution-based receiver.
What's the mic?
And how does this working actually? How that meter is controlled or something is happening with the feedback?
Oh, okay. So this is actually a current source, right? And you're pushing current into the resistor, right? And so you're heating the ring.
How that error thing is coming out of that loop?
How is the error coming?
Yeah, means the need to be either heated or need to be reduced that current amount, something like that. How is
so you have photo current coming out of this, right? And there's obviously modulation current, but there's also an average current, right? The average current depends on how much power you've actually absorbed in the channel, right? So let's say you received minus 7 dBm power, right? You don't know you're getting minus 7 dBm, right? Because you don't know a priori how much your receiver is going to get. So all you want to do is you want to maximize this power, right? So you sense the average current out of this photodetector, right? And then you apply the slope minimization because you don't have a reference to compare it. You can't say that I want 10 microamperes, 100 microamperes of current. You don't know if that's what you're going to get. But using this by trying to figure out whether you've actually locked to this point where the slope is 0, you can lock the receiver as well. That was the point of this slide. So all of this is just the circuitry that goes into implementing the slope detection algorithm.
how that delta is coming?
How this delta is coming?
Yeah,
So you see this. So in the digital backend, so this is actually all digital. In the digital backend, we introduce this error of delta H, right? It's very small, so it's not like a really large error.
Why is that calculation? Delta is calculation
Inside the digital backend. we apply a small dither. And this delta H is applied to whatever you would anyway control the ring with, right? So you need some amount of heat, let's say 10 milliwatts of heat to control the heater. So you would apply 10.xxx1. I don't remember exactly how small that is, but it's something so small that it wouldn't actually disturb your insertion loss.
Okay.
Yeah.
So when you perturb this,
Yeah.
is it happening at a characterization process, or is it
No,
happening?
it is actually background. It is actually background. You're always applying that little delta H plus delta H minus delta H because you want to continually calculate slope, which is why it has to be small enough that you don't actually change the H that you need to apply. And so it will introduce a small variation, but it's not large enough to cause eye closure.
Wouldn't that get averaged in a delta sigma modulator?
The delta H?
Yeah.
You mean where do you
See, you're passing it through a loop filter coordinate, summing it up and then sending delta sigma.
Right.
So even if you have a 4-bit, you have a significant averaging happening, right?
Yes.
So won't that get averaged?
Oh, so the dither, you have to adjust all the frequencies in the loop and ensure that your dither is actually getting through to that. So there is a relationship between figuring out the loop bandwidth and the frequency of the dither, and so it's not. You have to of course ensure that does not happen. Any other?
How do you actually co-simulate the CIC and PIC while doing the simulation?
That's actually a very good question. So we make models. So all the photonics is simulated in, I believe, these. I'm sure some people here will know. Yes. Yeah. And then we get models, right? And we add them to our cadence simulations, right? And that's how we simulate this. We also, I mean, at the initial stages when we are still, figuring out ideas, we use Simulink and do behavioral models. Yeah. So like behavioral models for the electronics, behavioral models for the photonics, and do it. This is at the at the link level when you're trying to simulate.
Model that you get is what, right?
Pardon me?
Model that you get from ANSYS into cadence.
Oh no, we develop these models ourselves. So it's just like the ring is modeled, for example, as an RC. But there's also something which is a Verilog model, which is nonlinear to capture the movement. So these are models that are built in-house. Yeah.
So basically, you're converting the physical model into an RC analog model.
Yeah, or a Verilog. I think it's not sufficient to describe it as an RC. So you have some Verilog model in there which captures this Lorentzian and its nonlinearity. Yeah.
So is that efficient? Because sometimes there are very minimalistic features which are not captured using these kind of models. Because I myself do sometimes.
Yeah.
Or waveguides and all.
Hmm.
But there are minimalistic features or some nano features which cannot be modeled using any of these. So
I mean, unless they're necessary for the for studying the broad effects that we're interested in, we don't necessarily need to capture a model to that degree of fineness. So, for example, in this case, you just, for example, for energy, you just need to capture the fact that the one level and 0 level are different, and the transition will depend on whether you're going from 1 to 0 or 0 to 1. So as long as that is captured, you don't have to capture the fine features of an MRI.
I'm sorry, I confused the QAM with the PAM last time, PAM4 and QAM4. So why are we not using QAM4 instead of PAM?
We aren't using coherent at all right now because we're able to get where we want to with intensity modulation. Coherent comes with a lot of overhead. You need an extra fiber to either laser forward or you need to do optical carrier recovery. So all of this needs to be developed. This is great for like those really long links where this is not a significant fraction of the total power. But for us, we need to put this near the XPU. Everything needs to be super efficient. Need to reduce the number of fibers. So we haven't looked into yet, but maybe someday we'll reach a data rate where coherent needs to be done.
Yeah, because I think some cases it can be better, right? Especially in the high speed links also. Or like, is it a problem?
So now, there is no. I don't have a definitive answer on this, but what I can tell you is, so coherent does give you this advantage in gain, right? Because you're multiplying it with a forwarded carrier. But some of that gain we are able to make up specifically inside Intel because we are using this integrated laser. So we don't have that additional coupling loss, and so we are getting a lot more power into our links than you would if you were trying to get it from an external laser. So some of that gain, we don't really need right now. But yes, it is. I won't say no. We are never going to do coherent because honestly, I don't.
Yeah, other problem with WAN is that the phase shift keeps on changing.
Okay. So I'm not very familiar with coherent. I only know these broad ideas which I can express to you. But
Yes,
you
that
can,
is pretty good. Like,
yes,
What was the power supply for 28 nanometers?
so our drivers run off of 2 volts,
Power supply
1.8,
was 2
1.8, yeah, and the other circuitry runs off 0.9. So our highest supply is 1.8.
Okay, got it. So that was my doubt. Like if you have low power supply, then how are you getting 2 volts out of the CMOS driver? So
No, we're doing.
VDD is higher.
Yeah, the VDD for the stack driver is higher. There are other topologies. I mean, it's not you don't have to go with the stack driver. People have shown, for example, people can take an MRM and bias it in slightly forward bias, and that improves the phase modulation efficiency a lot. Which means you can get a higher swing with low voltage, higher optical swing with low voltages, and you suffer in bandwidth. You can use, and so I think there is a paper from IMEC a few years back where they've done 1.5 volts with 1 volt on one side, half volt on the other. I think I may be wrong, but that's the paper. They wanted that for something like 1.5 volt, where you don't necessarily need to use a higher supply.
Will there be any impact of interior imperfections of the silicon BTs?
On the laser?
Yeah.
Well, so we measured a few, and that's the error that we get, plus minus 20 gigahertz, right? So that's my best answer for you right now. I could refer you to the paper if you want to read more about it, if they have written more about it. So. Oh yeah, so we had that question a little bit about 5 minutes ago. So we, I think people told me that what you use for Silicon-Photonics is ANSYS. Honestly, I didn't remember the name. But what we do for designing the electronics, we use these models that capture the broad effects like the Lorentzian nonlinearity or any dynamic nonlinearity in the ring that I talked about, and some RC modeling, pad capacitance, etc. We capture all of that and we put it as a block in our cadence simulations. And very early in this, in the picture, we may also use Simulink with behavioral models for both photonics and electronics. And the gentleman here did mention that you may not be able to capture very fine things with this, but all I meant to say there was that we captured what we needed. Yeah. I think the room is fallen for it.
Yes, let us thank Dr. Jahnavi again for a wonderful talk. We would also like to present a small token of thanks for both the speakers, Dr. Javed and Dr.
Thank you very much.
You can come from that side.
Yeah.